Right, today we're talking about Chapter 1, Section 1. Right? We're talking about differentiation. Chapter 1 is about differentiation. Let's start off. Let's start off over here. Let's snip this. Alrighty. So in this course, all right. So many of you that have signed up have probably already had a calculus course. All right. But for those of you that have not had a calculus course, you're going to see that the many years of your labor in mathematics courses, they're going to finally start paying off in this course. I know it seems kind of crazy, kind of ridiculous that it takes 13 years of schooling to get to this point, but the fact is, you just kind of have to pound that stuff into the memory bank in order to understand a lot of the stuff and a lot of the concepts we're about to go over in this particular course. All right, so let's start at the top. So differentiation, why it's important. In this chapter, we begin our study of calculus. The first concepts we consider are limits and continuity. We apply those concepts to establishing the first of the two main building blocks of calculus, differentiation. Differentiation is a process that takes a formula for a function and derives another function called a derivative. A derivative represents an instantaneous rate of change. Throughout this chapter, we develop techniques for finding derivatives and explore their many applications. So, really quickly, let's look at. I remember saying it. There we go. It says we apply those concepts to establishing the first of the two main building blocks of calculus. Okay. So, what that means is, up until now, you are familiar with your four main operations, right? Addition, subtraction, multiplication, and division. Right now, obviously, like exponents and square roots and stuff, those well, there are derivatives, I guess. There are derivatives of multiplication and division. So we really know those four operations. Well, what calculus is going to introduce to you is we're going to introduce you two more operations. All right, the first of which will be differentiation. So let's look down here and see where it says where it's used. Sales of iPads. So the number of Apple iPads sold per year in millions of units, T years after 2010 can be approximated by this particular equation right here. Okay. Now, interestingly, I do want to point out that these equations here, they're not just an arbitrary equation that you just come up with. These equations are built in a class called differential equations, which is after the calculus sequence. So you have that to look forward to, if depending on what route you're going. So it reads, find the number of iPads sold and the rate at which sales were increasing in 2017. Okay, so we look over here. So this is number of years after 2010. So obviously 7 years. Okay, so easily enough, you just put 7 into t over here. You plug the value 7 in for t, and then you just do the arithmetic. And then by doing that, by evaluating the function at 7, we see that we sold about 68 million iPads. Okay, that's I hesitate to say this. That's the easy part. That's what we've been doing a lot in a lot of classes leading up to this particular course. Okay. However, we want to know how much they were increasing by. Okay. And the way we do that is through calculus, the instantaneous rate of change. Okay, so I don't know if you can tell, but there is a little notation right here next to the n. Okay, it says n, and well, it could look a little better right there, prime. All right, just like little comma, and that stands for prime. Right, and that's where we're going to get into differentiation. Right, so that's just a little precursor to what we're going to be doing. So let's actually dive into what we're going to be doing. Right, so there's going to be a lot of reading here. Let's okay, so a lot of this does not necessarily have to be snipped into our right, we'll do example 1. Okay, so starting from top. All right, so this reads, uh, consider the pattern formed by the following sequence of numbers. 0.9, 0.99, 0.999, 0.9999, and then I'm not going to read the last one, and so on, right? So the numbers appear to be getting close to the number 1, yet never equal 1 exactly. Assuming that the sequence continues in the same manner, we could say that the limit of this sequence of numbers is 1, right? That makes sense. We're obviously approaching the number, we're obviously approaching the number 1 if we just kept going, right? We just keep adding a 9 and, getting closer and closer. Note that this sequence of number approaches 1 from the left. All right, let's continue. Approach 1 from the left, meaning that all numbers in the sequence are less than the limit 1. We write x and then the arrow. So we write x and then the arrow. Right. What that means is x approaches. You should be, I won't say should be, but this notation has been hopefully seen by you before in a pre-calculus course. All right. And then we're approaching some number. In this particular case, we're using the variable a. So approaches a, and then we're going to put a minus sign, meaning from the left. Okay. And of course that makes sense, right? If you look at a Cartesian coordinate plane, we know that the negative signs are over here and the positive, not negative signs. We know that x values are negative on the left and the x values are positive on the right. Okay, so continuing on. We read this as x approaches a from the left. To represent a sequence of numbers that approaches a from the left, thus the sequence, what we read before, and so on is written like we say x approaches 1 from the left side. And of course we can see that here, right? We're going from 0.9, 0.99, 0.999, and we're approaching the number 1, right? We're approaching the number 1 from the left side. From the left side, again, talking about if we're looking at the Cartesian coordinate plane. Okay, so if 1 was right here, right? As we are approaching from the left, we're getting closer and closer to 0.9, 0.99, 0.999. We're approaching 1 from the left. Okay. So on the other side, the following sequence approaches 1 from the right, 1.1, 1.01, 1.001, 1.0001, and so on. Right? We write that as x approaches a from the plus side. Okay, so we would say x approaches a from the plus side, right, from the right side. In this particular case, we're saying that x approaches the number 1 from the right side. Okay. And so that's the notation we need to get familiar with real quickly. Hopefully it's not too difficult right now. Okay. So that about sums that up. We're just going to go ahead and snip this entire example. There's not really much computation or anything that I need to be writing down. So we're just going to go ahead and put the whole thing here. All right. So example 1 reads, for each sequence, determine its limit. Rewrite the sequence in the form x approaches a from the left or x approaches a from the right. Right? X approaches a minus, x approaches a positive. Okay, so an a, I guess I could have not done this. All right, we can talk through. Obviously, you can read through those nice squiggly lines, but they're there. Okay, so looking at a, okay, we're at 2.24, 2.249, 2.2499, right, and so on. Okay, so it looks like we are approaching this. Looks like we're approaching 2.25. Okay. Also, it looks like we are approaching 2.25. Let's actually go ahead and put this off to the left. We'll make it a little more concise. Okay. And again, obviously the answers are down there, right? But it looks like we're approaching 2.25 here. Okay, and it looks like we're approaching it from the left side because obviously 2.24 and 2.249 and 2.2499, they're all on the left side of 2.25. Okay, and of course we can see that because our answer is already there. So B, 5.51, 5.501, 5.5001. All right, this looks like we're approaching what looks to be 5.5, but it looks like we're approaching it from the right side, right? Because we're getting closer and closer to 5.5, but it looks like we're approaching it from the right side. We're coming in from this way, okay? 5 point, oh wait, that's that. 5.5, oh yeah, that's right. 5.51's here, right? And then, right here on a very big number line, I guess, it would be 5.5001. And of course, it just gets messy, right? But it looks like we're approaching 5.5 from the right side. Okay. And then C, the last one. We have 1/2, 3/4, 7/8, 15/16, 31 32nds, 60 30, 64. Sorry, this doesn't seem too hard at all. It looks like we're approaching the number 1, but of course, it looks like we're approaching the number 1 from the left side. Okay, so this is just an example of limits. Well, not actually, I'm sorry, it's not an example of limits. It's an example of how our notation is going to work moving into limits, how we write the notation, and how we determine if we're coming in from the left side or the right side. All right. It's not really a brain teaser. You pretty much, I doubt many of you that are paying attention look at this and we're like, dang, I can't tell if we're going to 2.25 from the left or to the right. Okay, so hopefully that's not too insulting. If it is, I'm sorry. I didn't mean for it to be. Mainly meaning for it to segue into a conversation about how things are about to get harder. Okay, so so far on the previous examples, we talked about how we write the notation as we approach some number. Right? Now we're going to be talking about the limits of a function, which is basically the crux of chapter 1, section 1. Okay, so starting from the top, let's suppose we have some function. F of x is equal to 2x plus 1. That's nice. That's a nice, easy function. Where have those been all our lives, right? And let x assume the value in the sequence is 0.9, 0.99, 0.999, and so on, okay? So what we're saying is we're going to take this function, we're going to take this function, and we're going to evaluate it at some number, okay? This number is going to be 0.9, 0.99, 0.99999, and we're just going to see what happens. Now, obviously, you probably have a good idea of what's going to happen here, right? And that's the whole point of this. You have an intuitive idea of what's going to happen because of your background in mathematics, right? Well, as we move along here, we plug in 0.9. Well, 2 times 0.9 plus 1 is equal to 2.8. 2 times 0.99 plus 1 is equal to 2.98, and so on. And we see as the number that we evaluate gets closer and closer to the number 1, we get closer and closer to the number 3. Okay? And that is the notation that we're looking at. The notation being down here, we say the limits. For the record, whenever I write on the textbook, it's a little choppier than when I write on the actual blackboard. So you just have to bear with me. But the notation here is we say the limit as x approaches 1 from the left side of f of x, all right, that value is 3. And of course, that's what we see here. The limit as x approaches 1 from the left side gets to 3, and of course, that is seen here. Okay, but of course, that can be seen graphically, but we'll see that. We'll bust out the graphs here in a moment. Okay. All right, so on the same side, I won't say same side. On the other side, literally the other side, we have, now let x assume the values of the sequence 1.1, 1.01, 1.001, 1.001, and so on. If we evaluate that, right, it appears the numbers that we're evaluating at, it appears that we are getting closer and closer to the number 1, right? So we're getting closer and closer to number 1 from the right side. Okay, and as we approach 1 from the right side, we see that we are approaching the number 3. Okay, so same as before, what we're going to do is we're going to say the limits as x approaches 1 from the right side, okay, from the positive side of my function f of x is going to be equal to 3. So you see how, just a side note, see how it's like the turns are really sharp there. that, again, it has to do with me writing on the textbook. They're not going to be, they're not going to be that sharp, and they'll flow a lot better on the blackboard. But anyways, that's how we write approaching a limit from the left and approaching a limit from the right. Okay, down here. All right, so if we write x approaches 1 with no superscript plus or minus on 1, that indicates that x approaches 1 from both sides. Right? If both the left-hand limit and the right-hand limit exist and are equal to the same real number L, then the general limit, or simply just the limit L, in the above discussion, since the limit, and again, I'm saying a lot of words, I'm right here, since the limit as x approaches 1 from the left of f of x equals 3, and since the limit of x approaching 1 from the right of f of x is equal to 3, then the general limit as x approaches 1 from both sides exists and is written as just simply the limit as x approaches 1, no superscript, no plus sign or minus sign, limit as x approaches 1 of f of x equal to 3. This leads to the following theorem. Okay, this theorem is a super big deal in this course. Let's not do that. When I first took calculus, I remember that we had to prove this theorem. But I guess this textbook doesn't want us to, so we're not going to. Alrighty, so that takes care of that. Now let's go to graphical limits. Right, so we're at the end of the page. We're just going to talk about it anyways. So graphical limits, again, down here. So we're going to view the limits graphically. We let f of x equal to 2x plus 3. Was that the same function? Oh, it's 2x plus 1. Okay. So changing gears here. So we're going to have f of x equal to 2x plus 3, and we're going to select x values that get close to 4. In the table and graph below, we see that as input values approach 4 from the left, that is, are less than 4, the output value reaches 11. And as input values approach 4 from the right, that is, that are greater than 4, again, approaching from the right with the plus sign, right? The output values also approach 11. Thus, we say as x approaches 4 from either side, the function f of x equal to 2x plus 3 approaches 11. All right, so that was a lot to unpack. So let's go ahead and touch on it real quick. Okay, so we have our graph here. This is 2x plus 3. Okay. All right, now we are trying to approach. It looks like we're trying to approach what, 4? Yeah, it looks like we're trying to approach 4. X equals 4 right here. We're trying to approach x equals 4. Okay. Well, as we go along on the x-axis, okay, we're at negative 12, negative 10, negative 8. We're at 0, 2, and as we approach 4 from the left side, okay, our x values as we approach 4, 3.9, 3.99, 3.999. When we plug those into our function, when we evaluate the function at these numbers, all right, our y value, or the function at that x, approaches 11. See, 10.8, 10.98, 10.998. Okay, so the limit from the left side exists, right? Well, we do that from the right side. Of course, we're kind of out of room here. But as we're going down, 12, 10, 8, 6, and as we approach 4, right? 4.01, 4.001, 4.01, 4.1. As we approach 4 from the right, we also approach that same number, 11. Okay. So to sum up this example, since we have a limit that exists approaching 4 from the left side, and since we have a limit as we approach 4 from the right side, then it follows that the limit of f of x as x approaches 4 is 11. And you know something I did not do? I snipped it, but I forgot to talk about it. Oh, there we go. The theorem, okay? So it's one of those things that's like, no duh, but we put it into mathematical text, right? Furthermore, this last sentence kind of could be confusing, and we're going to unpack it a little bit more with examples later on in today's lecture, okay? But let's start from the top. So as x approaches a, the limit of f of x is L, right? So saying, as x approaches some a, we know that the limit of f of x, well, it's just going to be some L. I guess I don't have to write all that. where L is a real number. If the left-hand limit exists and the right-hand limit exists, and if both limits are L, okay, so if a left-hand limit exists and it's L, and if a right-hand limit exists and it's L, so basically meaning the exact same thing, then it follows that the limit, all right, and again, notice how this A does not have a super or a subscript, all right, then it follows that the limit of that function at that number exists, okay? So if we can find it going from the left, and if we can find it coming from the right, all right, if both of those criteria are met, then the limit exists, okay? Now, the second part here reads, the converse of this theorem is also true, okay? So if the limit exists, then it follows that the limit of f of x from the left side and the limit of the limit of f of x from the left side and the limit of f of x from the right side are the same, okay? So the converse saying, basically flipping this around. If we have a limit, then the left and the right side do exist, okay? Now, could be a little confusing, and I'm going to show you what I mean by that here later on in one of the later examples, but let's just put that on the back burner for right now. If the left hand or right hand limit does not exist, or if the right hand and left hand limits exist but are different, then the limit does not exist, which makes sense, right? So if we do not have a left hand or right hand limit, or if the right hand limit and left hand limit exists but are different, then the limit does not exist. Okay. Whew. Lots of limits, lots of limit words. Okay. This is gonna be another example of me just snipping. I promise I do the calculations, or the computation rather, in the course. It's just for something like this, I don't feel like putting. I'll explain myself here in a second. Hang on a second. Yeah. Okay. So real fast, I feel like I do have to explain myself about something here. You can I'm going to upload this obviously to YouTube, and you might have seen them already, but I do the computation in all my classes. It's just in this particular case, this would just be simply putting. I would be sitting here quietly, putting this into the calculator, and then writing pretty much the exact same thing. Okay, so I figured, I can cut that time out instead of me putting it into my calculator without you watching, because it's just be dead silence, and we'd get the same place, right? But I promise you that's not how the lectures are going to be played out most of the time. It's just the way it is right now. Anyways, let's move on. So example 2, we're going to let f of x equal to negative 3x plus 4. We need to find the following limits, okay? So A, we're going to find the limit approaching 2 from the left side. We're going to find their limit approaching 2 from the right side. And if these two do exist, we're going to find the limit approaching from the right side, okay? So obviously, this is the same procedure we've done up to now. We're just going to plug in values as we get closer and closer to the number 2 from the left side. Okay, again, that's what A is wanting. We're wanting to approach 2 from the left side. All right, and as we do that, we appear to approach the number negative 2. Okay, so as we plug in these values, it appears that we approach negative 2. Okay. All right, so similarly, we're going to plug in the value of positive 2. So we're going to get closer and closer to the number positive 2. Okay, so 2.1, 2.01, 2.001. As we plug those values in, it appears that we are approaching the number negative 2. That's good, because we were also approaching negative 2 from the left side, and now it's where we found out that we're approaching negative 2. We're approaching negative 2 from the right side. So since these two exist and are going to the same L, the same limit, again, going back here, as long as they're going to the same limit, okay, so as we approach from the positive side and from the negative side, since they're approaching the same limit, then that tells me that the function itself also has a limit. And the function itself, as we see, all we do is, if we plug in our values, well, actually, we're not plugging in values, I'm sorry, got ahead of myself. Since the left-hand limit and the right-hand limit exist, right here, and are both equal to negative 2, we conclude that the limit as x approaches 2 exists and is negative 2. Okay, and of course we can see that graphically over here. These right now these examples are kind of in the no-duh scenario, right? We're going to see how different scenarios do play out, but we'll just get an idea here. Okay, so again we can see over here as we approach 2 from both the negative side and both the positive side, we do indeed approach -2, and green on white is probably not a good idea. Right. Alrighty, so it reads, so example 3 is where we get to have a little bit of fun. So it reads, in example 2, note that f of 2, right, the function evaluated at 2, is equal to -2. It is true that in some cases, finding the limit of f of x as x approaches a can be as simple as evaluating f at a directly. So let's go back and see what they just said. Remember how I said I jumped ahead of myself? That's what I'm talking about. So if we were to do this, okay, look at C. We say, okay, so the limit as x approaches 2 of f of x. Well, f of x is this, right? So all we would do is plug in 2, right? -3 times 2 is a -6. -6 plus 4 is a -2. And then we could say that we do indeed have the limit at -2. Okay, so that's what the top sentence is saying, right? And then asking the question, can we do that for all of them, right? So this quote shortcut is permissible under certain conditions, which we'll discuss in the next section. But for now, we're going to explore limits using numerical and graphical methods that examine the behavior of a function near an x value. Okay, so example 3 is a good example of why we can't just do that. By the way, I snipped these out because number 1, I do the computation when necessary, and number 2, they're notes for you, right? So whenever I do upload these, I upload the PDF of all the notes that I just did in class. Put that here. Yeah, that'd be fun. Alrighty, so alright, so example 3, it reads, let f of x be equal to x squared minus 1 divided by x minus 1. We need to find the limit as x approaches 1. Okay, so same procedure we did before, right? What we're going to do is we're going to plug in values approaching 1 from the left side, right? So 0.9, 0.99, 0.999. And as we do that, we see that we get to the number 2. Okay, and as we plug in values, as we approach the right side, we get 1.1, 1.01, 1.001, so on and so forth. We end up getting 2. Okay, so since the left hand and right hand limits exist and are equal, we conclude that the limit of f of x as x approaches 1 is 2. Okay, so we conclude that this is indeed the case. As we approach 1, positive 1 in this function, we have the limit of 2. Okay, but really quickly, let's check something out. Let's see, well, I think it was x squared minus 1 divided by x minus 1. Okay, cool. So this is what the function looks like. Okay, which is fine and dandy, all right? But in our example, we wanted to find what happens as we approached 1. Okay, we want to know what happens as we approach 1. Well, graphically, it's obvious, right? As we're going left to right, at -2, it's close to -1. Yeah, at -2, it's -1. At 0, it is 1. But as we approach 1, let's go over here. We're going to approach 1. Boom. Oh, I guess there it is. As we approach 1, we are actually undefined here at 2. Okay, so real quickly, pay attention to the dot. Notice how my dot is solid. This dot going up and down my line, it's solid, right? And of course, we know from previous courses that solid means that we're continuing through the process, right? We're continuing through the graph. But right here at 1, right here, oh, well, notice how it's open. It's an open circle, which means there's a hole in the graph. Okay, there is a hole in the graph here at 1. Right? It's undefined. What happens at 1? Well, that's obvious, right? We look over here at this equation, okay? Well, if we plugged in a 1, well, 1 minus 1 in the denominator, that's 0, right? And that's why we indeed do have undefined at 1. Okay, so I won't say to wrap all this up, but to kind of tie all this together, we see that if we were to have just evaluated this function at 1, we would say it's undefined. I'm sorry, evaluated that function, the limit of that function at 1. All right, obviously if we evaluated the function at 1, it is indeed undefined. But if we evaluated the limit of that function at 1, we would say that it's undefined. But that's not the case. The solution is actually 2. We are approaching 2. We're approaching it. We don't get there, but we're approaching it. Okay, and so that's how, let's go back to the text. That's how up here, remember I said finding the limit of f of x as x approaches a can be as simple as evaluating f at a directly. Okay, we obviously see that that is not the case. We cannot just simply evaluate at that point directly because, again, in this particular case, we would have gotten undefined. And of course, the solution is not undefined. So I think that's pretty interesting. All right, we'll put the summarization there. I kind of like the summaries. We'll put this down here, put the graph up here. Okay. All right, so next up we have everybody's favorite, the piecewise defined functions. All right, so how much can I snip of this? Let me put this there. Okay, that's not as good as it's going to get. All right, so starting from the top, consider our example. Consider consider the function h. Okay, this is h of x. The function's name is h, and the variable is x. All right, so h of x is 2x plus 2 for values of x that are less than 1, and 2x minus 4 for values of x that are greater than or equal to 1. Okay, we want to find the limit as x approaches 1 of our function h of x. Okay, so what we're going to do is approach 1 from the left side. Okay, so we're going to approach 1 from the left side, right? 0.9, 0.99, 0.9999. It appears that when we approach 1 from the left side, we appear to get closer and closer to the number 4. Okay, and of course that's what we can see here. Right, now next up, as we approach 1 from the right side, right, 1.1, I'm sorry, 1.01, 1.001, as we approach 1 from the right side, it appears that we're getting closer and closer to the number -2. Okay, getting closer and closer to the number -2. Right, so since these two numbers, maybe blue will show up, since these two numbers, okay, 4, -2, since they are not the same, we can conclude that the limit of h of x as x approaches 1 does not exist. Okay. Real quickly down here, note that h of 1 is indeed equal to -2 though. Okay. So h of 1 has a solution, right, when we evaluate at 1, but the limit at 1 does not exist. Okay. And of course h of 1 has that solution because if you recall from your piecewise functions, if 1, we'd be using this equation, right? Because 1 is equal to 1, right? 1 is greater than or equal to 1, rather. And if we plugged in a 1, we would end up getting negative 2, right? 2 times 1 is 2, minus 4 is negative 2. Okay, so again, you can't just evaluate at that value, right? You have to do the left-hand limit, and you have to do the right-hand limit. Okay. Down here, the existence of the limit as x approaches a of f of x does not require that f of a exists. If f of a does exist, it does not automatically follow that the limit of x approaches a of f of x equal to f of a. And we're going to see that in example 5. I just said a lot of words. I can tell right now I said it really too fast. I'm sorry. We'll get to example 5 though. All right. Okay. Well, I forgot about the wall method. We'll snip this real quick. All right. The wall method's pretty good. Basically, it's basically what you do is if you're able to graph it, right? If you're able to graph it, you can see that we are not well. No, don't want to use the word continuous because we're not at continuous yet, but we will touch on continuity quite a bit in this particular course. But for the sake of it, I'm going to say it. Notice how my line is not continuous there, right? What I have to do in order to continue to trace this graph is I have to take my pen off the graph and then resume down here. That's basically what the wall method is saying. All right, since there's man, I don't want to give away too much, but I'm going to use the same words I'm going to use later. Since I have to make a jump, then we know that the limit does not exist. Okay, so that is the wall method. Again, it's one of those things where you just kind of look at it and you're like, oh, okay, that the limit obviously does not exist. All right, next up. Okay. So example 5, it's another piecewise function, right? So consider the piecewise function defined as follows. So this function's name is g, and the variable that we're using is x, okay? So it is equal to 5 when x is equal to 1, and it's equal to x plus 1 for values that are not equal to 1, okay? So first of all, it wants us to evaluate at g of 1, okay? Well, this is pretty easy. Well, at g of 1, so since we're evaluating at 1, we're going to be using this function, okay? So g of 1 is simply going to be equal to 5, right? So whenever we use the number 1, which is being asked right here, we're going to be using that first the top function of the piecewise function, and we see that it is indeed 5. Okay. Next up, we want to find the limit of this function as we approach from the left side and approach from the right side. And again, now here's the thing. We could do this, right? There's nothing wrong with that. There's absolutely nothing wrong with this, doing it, with your calculator. But if you're able to graph it, it also helps. So since we've done it algebraically so far, let's just go ahead and do this one graphically. Okay. So as we're approaching, and again, we're wanting to find the limit as x approaches 1, right? So as we approach this limit, as we approach 1, so we're going up, 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 and 1 is right here. Okay, this is where x is equal to 1. So as we are approaching, it appears that we are approaching the value of y is equal to 2. Okay, so it looks like we're approaching 2 as we approach 1 from the left side. And as we approach 1 from the right side, it looks like we're also approaching the number 2. Okay, so we can say that the limit is 2. Okay, so again, another example of how we could evaluate it at that value of 1, but we would get 5, okay, because that we're following along what the piecewise function is. But when we evaluate the limit, we evaluate from the left side and we evaluate from the right side, we see that the limit as we approach 1 is 2. Okay, and again, just another example of how we cannot just simply evaluate at that particular number like that we're used to. Okay, we're used to problems like this. We say g of 1, well, that's easy. I plug in 1, I get my solution back. We're not doing that. We're finding the limit. We're finding what happens as we approach that graphically. All right. Let's see. How else I put this? The I'll just continue. Sometimes I feel like I can ramble too much, which, for the record, if you do watch these videos, I would highly suggest putting the speed at 1.5 speed, because, like I said, I do ramble quite a bit. Not 2 speed though. 2 speed's a little too fast. 2x speed. All right. So next up, I obviously, I mean, I wouldn't love calculus if I didn't enjoy mathematics, but um, I obviously do enjoy calculus, because what I think is fun about calculus is you get to play with the concepts of infinity, right? Now, in this particular course, not as much, but if you were to go on and take calculus 2, you'll get to play with infinity a lot more. Strange things happen at infinities, and it's really cool to check those out, right? In this particular example, this particular class, maybe not so much, but playing with infinity, I think, is a pretty cool thing to do. More rambling. Sorry. So anyways, let's limits involving infinity. Okay, so limits also help us understand the role of infinity with respect to some function. Example 6, we're going to have some function, let f of x is equal to 1 over x minus 2. Okay, so A reads, find the limit as x approaches 2 from the left side of my function. Find the limit as x approaches 2 from the right side of my function. And then C, does the limit exist, why or why not? Okay, so here are the two methods, right? The first method right here would be doing it algebraically, and the second method here would be doing it graphically. Okay, so let's go ahead and look at the algebraic method. We've done it a lot already today, but let's look at it again. Okay, so as we approach 2 from the left side, right, 1.9, 1.99, 1.999, 1.9999, right? As we approach 2 from the left side, our function appears to be growing, well, exponentially, right? 10, 100, 1,000, 10,000. I bet if we put another 9 on there, we'd have negative 100,000, right? Because we're just adding a 0. Okay, and then we add another 9, we'd be at negative 1 million, and so forth. Okay, so it appears that this is growing very fast without bound. Okay, and if we approach 2 from the right side, 2.1, 2.01, 2.001, 2.0001, same thing, except we're not going negative, we're going 10, 100, 1,000, 10,000, and again, I bet we would have 100,000 if we added another 0, 1 million if we add another 0, of course the 0 being in front of the 1, and we would continue to be growing without bound. Okay, so for A, actually no, let's not do that yet. I said we're going to do it algebraically. Now let's do it graphically. Okay, so let's approach 2 from the left side. Okay, so we approach 2 from the left side. We're going here, and we're shooting straight down. Okay, so we're shooting straight down. One moment. All right, I'm back. We're shooting straight down, and of course, you probably remember from your college algebra or pre-calculus days that we're going down, we're shooting down to infinity, right? This line right here we know as the vertical asymptote, right? Well, we're shooting down here to infinity, and we're shooting up here to infinity. Okay, so pretty much exact same thing we said here. So what does that tell us? Well, that tells us that the limit as f, let's actually write it out. So right? So the limit as x approaches 2 from the left, right, of my function f of x, okay, it appears that limit is negative infinity. Okay, there is no number that this is going to be going to. Right, we're going down. These numbers going down. There is no number that we are going to that it will eventually stop at. Okay, and I'm just going to fix this negative infinity here. All right, and B, approaching it from the right side, well, we have the same. We run into the exact same problem. Oops. Okay, we run into the same problem. We are approaching infinity. Okay, since these two numbers, I'm sorry, since these two numbers are not the same, then we can say that the limit of this function at the value of 2 does not exist. And of course, that's what this last sentence is saying. Right? Since they are not the same, the limit does not exist at the number 2. Okay. Now we can see obviously at any other number here, it appears that it exists, right? At any other number it exists, but at 2 it appears that it does not exist. Excuse me. Okay. Example 7 is more of the same. Pretty sure. Let me see if it's. No, it's not more of the same. Okay, good. I'm glad I checked that out. Okay, so example 7. Again, we could look at it either algebraically. Okay, there we go. Either algebraically or graphically. Okay, doesn't matter which, but in the end, I mean, it's up to you. If you have a graphing calculator, graph it. If you don't, then do it algebraically. Okay, but obviously graphing it is so much easier, in my opinion, right? And let's just examine it graphically. So this particular problem, let f of x equal to 1 over x. Find the limit of as x approaches infinity of f of x, and find the limit as x approaches negative infinity of f of x. Okay, cool. So it appears that as we approach, or we're going to go infinity first, as we approach infinity, all right, it looks like we're getting closer and closer to 0, right? So that's pretty easy. And as we approach negative infinity, we also approach 0. So no, that's it. On the other side, if we didn't do it graphically, we did it algebraically, again, you'll get to the exact same solution. It's just, you know, it may have to plug these numbers in, right? If we plug in 100, right, as x approaches infinity, if we plug in 100 right here, right, that is 1 over 100, or in other words, 1/100th, right? If we plug in 1,000, 1 over 1,000, which is 1/1000th, and of course you could tell that we're also getting closer to 0. And the same on the negative infinity side. So if you have the graphing available to you, do it. If not, then you're going to have to do it algebraically. But I will say, once we get out of this chapter, uh, no, I'm not going to say that. I don't want. I jump ahead too much. If you don't want to spend money on a graphing calculator, check out Desmos. It's free, just desmos.com, and you can graph things. Right. All right, so let's move on. There was something I wanted to talk about, actually. Okay, so what was I going to say about this? Okay, kind of. All right, so notice. Do you remember how we had problems where this would be true and this would be true, but we didn't. But the problem did not have a limit. Okay, for example, uh, hmm, you know what? Scratch that also. I have all these ideas of what I want to say in the lecture and I forget them all. I'm not even old. All right, so last one, pretty sure. 4 parts, okay. All right, yeah, this is 4 parts. All right, so there's gonna be lots of snipping, so give me a second. All right. Actually, well, no, I'll keep it in the notes. trying to figure out how I want to do this. Okay, we'll just put b over here. Okay. All right. So, example 8, we're going to consider the function f given by the function f of x equal to 3x minus 5 over x minus 2. Right? So this wants us to graph the function and find each limit if it exists. So we need to find the limit as x approaches 3. Okay, so it says graph the function, find each limit. So look at the graph here. Okay, here's the graph. Right? As x approaches 3. Okay, so let's go ahead and approach it from the left side. So if we approach 3 from the left side, coming down, looks like we approach it, we get to it about right here, right? And if we approach 3 from the right side, we get to about right here. And it's kind of hard to see, I know, I'm sorry. Right? But it appears graphically as we approach 3, we approach the number 4. Okay? So as we approach 3 from the left side, we approach 4. As we approach 3 from the right side, we approach 4. Okay? So therefore, we can say that the limit of f of x as x approaches 3 is equal to 4. Okay? Well, what about the number 2? Okay? Well, here's 2. So as we approach 2 from the left side, well, it looks like we've already done this problem, haven't we? Right? As we approach 2 from the right side, it looks like we go down to negative infinity. And as negative infinity, and as we approach 2 from the right side, it looks like we approach positive infinity. Okay? So since we are approaching negative infinity from the left and positive infinity from the right, then we obviously do not have a limit because the two limits are not the same. Okay, and I guess I didn't need to snip C and D, but it's on the next page. And like I said, these will become PDF files for you to download. But the limit of f of x as x approaches infinity. Okay, so as we approach infinity, okay, so as we approach infinity, it appears that we're getting closer and closer to the number 3. Okay, and well, I mean, just take my word for it. I mean, I guess we can look at it, right? Where are we at? 3. Okay, and as we approach negative infinity from the are going to as we approach negative infinity, as we approach negative infinity, it appears that we are also getting to the number 3. Okay, so the limit for C and D do exist, and that limit is indeed 3. Okay, so I guess that kind of covers everything we did, right? We're asked to find the limit of a value that does exist. We're asked to find a limit of a value that does not exist, and we're asked to find limits of the infinities. What happens at the extreme ends? Okay. What was I going to do? Oh yeah, next, and again, that's just C and D. And I believe that does conclude it. We're going to put the section summary here, though. There we go. All right, so that does conclude today's lecture.